Welcome everyone, this is Professor Ridge, and today's lesson is on real numbers, the algebra essentials. Okay, so let's start with the first learning objective, classifying a real number as a natural, whole, integer, rational, or irrational number. Okay, the first set of numbers that we'll talk about is what's called the natural numbers. And if you think about it, when in human development, the first use of numbers was probably to go out and count things. So we call those the natural numbers or counting numbers. And they're simply the set that of numbers that we use for counting. So the natural numbers are 1, 2, 3, 4, 5, and so on. Then the next set of numbers is whole numbers. Now, believe it or not, this took many, many years to come up with a symbol to represent nothing. So the only difference between the natural numbers and the whole numbers is the number 0 that represents nothing. So 1, 2, 3, 4, 5, so on. Next, we wanted to introduce numbers to represent negatives, right? Owing. And so if we add the negative numbers of these, or we call them the opposites of the whole numbers, so the opposite of the whole numbers, -1, -2, -3, so on, that set gives us the integers. So the integers are the negative of the whole numbers, so -5, -4, -3, -2, -1, 0, plus the whole numbers. So basically we're adding just the negatives to this whole number set. 1, 2, 3, 4, 5, so on. Okay, next we're going to add the numbers in between. Not all of them, but for instance, if I wanted to have a portion of 1, 1/2, 1/3, or 1.5, 2.7, those numbers we call the rational numbers. So the rational numbers include all the integers plus those fractions that are in between. Now, as far as notation goes, for these sets, this is what we call roster notation, by the way, where we just explicitly list every member of the set. So for rational numbers, you can't list them all, so we have to describe it. And this notation we're using will be called set builder notation. So you're going to describe what does it mean to be a member of the set. So to be a rational number, it's basically a fraction. So you got m over n. It's a ratio. That's where rational comes from. And then m, and this straight bar means such that. So this is the set of all m over n such that m and n. So now we're describing what m and n are. So m and n are integers, and we can't divide by 0, so we want to make sure n's not 0. Okay, so that describes the set of rational numbers. So again, some examples for rational numbers would be like 1 over 2, 1/2. So you see that fraction. And again, all the integers are part of rational numbers because you can take every integer, like 7, and write it as a ratio of 2 integers. So that's a rational number. So it includes all the integers. Same thing for like -3. You can write -3 is -3 over 1. So you can write any integer as a fraction by putting it over 1. So all the integers are also rational numbers. Now the next set is called the irrational numbers. Irrational numbers. Now this one is basically simply a set of all h's, is the way this book uses, where h is not a rational number. I should add that, but it has to be a real number. It's a real number that's not rational, and we'll get more into that later. So what is a rational number? Or irrational number, sorry. Basically, it was kind of discovered if you had a square, so the Greeks did a lot of geometry. I believe they're the first one that noted, maybe not. So if this side was 1, 1, and they figured out this number, you couldn't represent the length of this diagonal by anything that was a basically a ratio. No matter how you scaled it, you couldn't make this a ratio of two integers, right? So this is actually square root of 2, that length. And square root of 2 is what we call an irrational number, and it is, if you put it in decimal form, I should say about equal to 1.414, and it goes on forever and ever and ever. It's a non-terminating. This is something you might want to real. All right, let's look at example 3 from the text. Differentiating rational and irrational numbers. Determine whether each following number is rational or irrational. If it's rational, determine whether it's terminating or repeating decimal. Now, probably the easiest way, right, if you just got a calculator, square root of 25 is just 5. It's a whole number. So this is equal to 5. So you can see that it's a terminating decimal. If you think of it as a decimal number, it stops. It's just 5. Okay, so that's a term that's rational, and it terminates. It's a terminating decimal number. Okay, 39 over 9. If you punch that in your calculator, it will be. Here, let me get a calculator open here. So Desmos is my one of my favorite graphing calculator programs. You just go to desmos.com, and it's free. There's no charge for it, so I actually use this all the time in the classroom. Alright, so if I wanted to do 33 divided by 9, I mean, you can see that's not going to be a whole number. And then you can see it's 3.6666, and it's going to repeat forever here. The calculator's rounding it, but it's 3.66. So that would be a repeating decimal. What was it? 3.6666. Put a line over the 6, right? So again, it would be rational. So to be irrational, it needs to be non-terminating, non-repeating. So it has to go on forever, and there can't be a pattern in it. If we did square root of 11, you can see in Desmos here, let's do square root. You just type, there's a toolbar at the bottom. You can hit square root, or you can type SQRT, square root of 11, 3.31662479036, and it'll just keep going forever and ever and ever. So that one is irrational, and it's non-terminating. Okay, 17 over 34. So one thing to know too, if it's written as a ratio of two integers, you know that's the definition of a rational number. So it's obviously going to be either a terminating decimal or a repeating decimal, right? So 17 over 34. Where did my decimals calculator go? Hang on. All right, so if we put in, oh, we don't want square root, so we want, what is it, 17 over, you just hit the divided by 34. And, oh, that is 0.5, so that is, I'm laughing at myself, I should have recognized that. I'm usually pretty good with halves, right? That's 1/2, so 0.5. So obviously that terminates. And then this one, it's 0.3033033330. So even though that there's a pattern in there, it's not technically repeating. So that one we would consider irrational. Okay. So that is irrational. So when we say repeating, we mean like 2 digits repeat forever or 3 digits repeat forever. But this is, you can't say 3 repeats because then it would be 3333. You can't say 303 repeats because that would be right to there, but then that gets messed up. You see? So that would not be considered a repeating decimal. All right, let's move on. Real numbers. So the sets of rational and irrational numbers together make up the set of real numbers. So we can represent every real number on what we call the real number line, and we can break it into 3 subsets. We can have 0 all by itself, and then everything to the right of 0 would be the positive real numbers, and everything to the left of 0 would be the negative real numbers. So 0 is what we call the origin, or if it's 0, right, it's neutral. It's not positive or negative. Everything to the right is positive. Everything to the left is negative. So if we were to, again, every point on this represents a real number. So for instance, this might be right here, might be 0.5. Oops, let me get in my, so here 0.5 or 1/2, same thing. So that point is 0.5. The square root of 2 is about 1.4, so roughly there, just kind of eyeballing it. So which is about 1.4. If you wanted to do 9 halves, so 9 divided by 2 is 4.5. So you can think of right there would be 9 halves. So those are all positives. If I did a negative, say negative 1/3, would be right about there. Okay. And then if I did negative square root of 5, hang on. Okay, that's about 2.236. So negative, so right roughly there. So again, every real number can be represented by a point on the real number line. Anything to the right of 0 is positive. Anything to the left of 0 is negative. 0 is neutral, doesn't have a sign. It's neither positive nor negative. All right, let's look at example 4, classifying real numbers. Classify it's either positive or negative, and either as rational or irrational. So again, this minus sign you can interpret it as also negative. So negative 10/3. That's a rational. It's a ratio of 2 integers. So that would be, let's see, as either positive or negative, and rational or irrational. So that would be a negative rational number. Okay, so negative and rational. Oops. negative, that's horrible, negative, and rational. Okay, square root of 5, well, we just talked about that. It's 2.236. It goes on forever. So that's irrational. That's positive, right? There's no negative sign. So that would be positive and irrational. Oh, and then does it lie to the left or right of 0? So if it's negative, it's to the left. So this would be this one to the left and this one to the right. 289. Now you got to be careful just because you have the square root, right? If you know your squares, this should be kind of say, hey, that's a perfect square. So if I were to punch it into a calculator, you're going to get a whole number, which is rational. So let's see here. So if I do square root of 289, that's 17, right? And then the negative in front would just make it negative 17. So that one is, okay, I'm not going to write it, just say it. So this one will be negative and irrational, no, rational. Maybe I should write it. So it's negative and rational, and then it'll be to the left of 0 on the number line. Pi, all right, the next one here, pi is, represents the number, pi represents the number roughly 3.14159, so on. Okay, and it is an irrational number. And then if you multiply that by 6, it will still be an irrational number. So in fact, let me show you on here. So if we do negative 6 times pi, and you can see this is going to be a non-repeating, non-terminating decimal number. So that one is irrational, and it's negative, so it'll be to the left. And then the last one, do we have any pattern in here? No, there's no repeating digits, and it's ... so it goes on forever. So that one will be irrational, and it's positive, and it'll be to the right. All right, I always like to look at this slide here. So if we think of the real numbers as the subsets of the real numbers, we started out with the natural numbers. That's this inside one here. So that was the set of numbers that we use for counting. And when you start counting, you start with 1, not 0. So 1, 2, 3. Then we talked about, all right, let's add in 0 to the set. We called that the whole numbers. So the only thing in this set is extra, is 0, right? So it includes all the naturals plus 0. That makes the whole numbers. Then we added all the negative numbers. That gets us the irrationals. And we're using I for irrational, W for whole, N for natural. And then the set Q is the set of rational numbers. So that's all the fractions that you can write as a ratio of 2 integers. Okay, and then everything outside of that are, so basically this circle, everything inside the biggest circle there, or oval, I should say, is rational numbers. So that includes all the integers, all the whole numbers, and all the natural numbers. Did I say I was irrational earlier? It's I is for the integers. Okay, some books use different letters. Anyway, doesn't matter. So anything that's outside the biggest circle, so inside the biggest circle are all the rational numbers, and then outside would be the irrationals, and together everything in here plus everything outside would be the real numbers. So the the universe in this case would be the real numbers. Later in the text we'll talk about imaginary. So you got the real and the imaginary. But for right now, we're just talking about real numbers. And so this is kind of how it splits up. So again, a real number can either be one of two things. It could be rational or irrational. It can't be both. But as far as rationals, you could be a natural number, a whole number, an integer, right? Those are all included in rational numbers. So for instance, 1 is a natural number. It's also a whole number. It's also an integer, and it's also a rational. Okay? So these are considered subsets when they go inside like that. Okay, let's move on to this next objective, perform calculations using order of operations. The order of operations, or operations in mathematical expressions, must be evaluated in a systematic order, which can be simplified using the acronym PEMDAS. Now be careful with this, because when I hear lots of people talk about PEMDAS, or you can use please, excuse, my, dear, Aunt Sally. The problem is there's basically 4 levels of precedent for doing order operations. Multiply and divide are considered the same priority level, right? So you don't necessarily multiply first, then divide. So the tiebreaker, I wish they wrote it in the book here, the tiebreaker is from left to right. And then the same thing for addition and subtraction. And we do a couple examples, I'll show you what I mean. But it's really important that you remember it's multiply and divide are on the same level. Right? So think of it as 4 levels. You're going to do everything in parentheses. Now parentheses, you can actually broaden that term, and it's grouping symbols. So it could be parentheses, brackets, the fraction bar is a grouping symbol. Okay? Then you do all your exponents, and then that's the second level. And then the third level, you do all the multiplication or division from left to right. And then addition and subtraction is your 4th level, so that's the last. And again, from left to right. Okay, so the next little box in the textbook did clarify this a little bit. So again, think of it as 4 levels, right? First, you're going to do anything within grouping symbols. So that's the parentheses. Let's write down. So it could be parentheses, it could be brackets. Usually you use like these for nesting, like this. If you had parentheses within parentheses, you would use brackets just to help distinguish it. Braces, right? Absolute value. I'm not going to write that down. The division bar, fraction bar, it separates into a numerator and denominator. So it groups it into those 2 things. Then your second step, simplify expressions containing exponents or radicals. So radicals, we'll talk about that later too. Radicals can be thought of as an exponent, as a fraction exponent or a rational exponent. And then you're going to perform any multiplication division from left to right, as you can see right there. And then once that's done, you're going to go to the next step and do add and subtract from left to right. Okay. Okay, so let's look at example 6 from the textbook. A, we want to use order operations to evaluate the expression. So if we look at this, so again, we're going to start with grouping symbols. So we got to do inside the grouping symbol. Okay. So inside grouping symbols, this is something else we should mention. You follow order operations. So if here's a grouping symbol. If there's another grouping symbol inside, you're going to do inside there first. So let me show you. Okay. Let me just show you real quick what I'm talking about. Let's say we had something like 5 plus 2 times 3 plus 4 in parentheses like that. So this is a grouping symbol, and then we're going to do inside this grouping symbol first. So we're going to do that first, get an answer. Okay, and then we're going to work from there. So that will get us 5 plus 2 times 7. So you can replace, if you have a number next to a parenthesis, you can replace that with a times once you make this one number. Okay, now in here, we're going to still follow order operations. So there's no more grouping symbols. There's no exponents. So then we're going to do multiply and divide from left to right. So that's a plus sign, not a divide. So 2 times 7 is 14. So 14. And then 5 plus 14 would be 19. And then once that's one number, you can drop the parentheses. Now if there's a number right in front of it, you could put you would put a times. So if this was like 3, if I had a 3 out here, then it'd be 3 times 19. All right, so inside this parenthesis, we do 3 times 2 is 6. And then inside this parenthesis, we do 6 plus 2, which is 8. And you can leave this as with the parentheses, or I could drop the parentheses and put a dot there for times, or I can just in my head think 4 times 8. All right, so we're done with grouping symbols. Now, so when I say grouping symbols, meaning there has to be more than a single number in it, right? So if I have a single number in it, then you can kind of basically, you can drop the grouping symbol. Unless you have other things like, you got to be careful with the exponents. So this is 6 squared. 6 times 6 is 36. And then 4 times 8 is 32. Oh, I'm skipping a step. Okay, so now we did the exponents. Okay, then we're going to perform any multiplication and division from left to right. So I'm going to do this one. With a little experience, you'll know that, yeah, I could have done it then. And then 36 minus 32 is 4. And that's our final answer. All right, let's look at another one. Okay, so we'll look at C. This is example 6C in the book. So we got grouping symbols. Remember I said the absolute value grouping symbols, so we need to take care of that first. So 6 minus the absolute value. Now 5 minus 8, if you forgot your rules, right? Subtract means add the opposite. So I'm thinking of this as 5 plus a negative 8. Signs are different, so I subtract. 8 minus 5 is 3, and I take the sign of the larger absolute value number. So 8's bigger than 5, so I take the sign of 8. So that would be negative 3. And then 4. Okay, so we're still undoing grouping. So that grouping symbol's done. Now here's another grouping symbol. So I got to do this one. 4 minus 1 is 3. Okay, now you got to be careful here. The absolute value of negative 3 is just positive 3, or just 3. You can think of it as that. And then remember, I made this one number, so I can drop the parentheses, but if there's something attached to it in front there, I got to put a times. So it's 3 times 3. All right, so grouping symbols are done. Now step 2, we're going to do anything that has exponents. There's no exponents. And then we go to step 3, multiply and divide from left to right. So here's the times. So 3 times 3 is 9. Okay, so that step's done. Now add, subtract from left to right. So we get 6 minus 3 is 3. Plus 9 is 12. Excuse me. Okay, so that's my final answer there. I guess I could be putting equals over here. I'd like you to box your answer or circle it when you complete a problem. Okay. Okay, so example 6D. So now notice this has a big fraction bar here. So that's a grouping symbol. So I got to treat the top, the numerator, the bottom, the denominator, think of them as two separate problems. So that's in my first step. So on the top, so basically if I write this out without the fraction bar, it's basically the top in parentheses divided by the bottom in parentheses. That's the way you write it. Okay, so let's look at the numerator. So you can kind of think of it as two separate problems here. So let's see, 14, okay, so there's, in the numerator, there's no grouping symbols. There's no radicals, so I'm going to do multiply, divide from left to right. So 3 times 2 is 16. 6. Okay, and then that's done. So now we're going to do subtract from left to right. So 14 minus 6 is, what is that? 8. Yeah, let me. 8. Okay, now on the bottom, again, so we're grouping symbols, so we're doing the bottom group. Inside that grouping symbol, we got to do order operations. So let's see, exponents. So 3 squared is 9. We leave everything else the same. And then, okay, exponents are done. Now we're going to do multiply, divide, left to right. So 2 times 5 is 10. So now we got 10 minus 9. Okay, and then we got to do add, subtract from left to right. So 8 over, leave everything else the same. 10 minus 9 is 1. Okay, now, so basically we did the numerator, we did the denominator. Now we're going to divide these two numbers. So 8 divided by 1, which is just simply 8. That's our final answer. Alright, so let's look at E now. Alright, so we got a grouping symbol here around the 5 times 3, a bracket, another grouping symbol, and then nested inside that one, there's this 6 minus 3. So we can kind of think of them as, here's another way to think of it. It's not written in there. You could think of, whenever you see this, you could think this as 3 separate problems. That one, that one, and that one. Okay. So for the first set, I got to do inside the grouping symbol. 5 times 3 is 15. And then now, since that's one number, I can drop the parentheses and put times 15. Now in this grouping symbol, we got minus 2. Inside here, I got to do 6 minus 3 is 3, and I can drop that parenthesis. And this one, there's nothing to do, so just write it down. Okay. Now we're still working grouping symbols, so I got to make this, take care of this. So in here, I did the grouping symbol. Now I'm going to do exponents. So I got to do 4 squared first. Again, if you want, you can go ahead and do 7 times 15 and make that one number. But we'll come back to that. And then 3 minus 4 squared, 16. And then 3 minus 16 is negative 13. So again, it's 3 plus negative 16. You got a positive and a negative. Subtract. 16 minus 3 is 13. And you take the sign of the larger, which would be negative, which would be 16. So it'd be negative 13. And plus 1. Alright, so now we're going to, okay, so our next step is, let's see, we did all the grouping symbols. So this is one number. I can drop it and put times, but since this is negative, I'm going to go, I'm just going to leave it the way I have it written. Okay, so we did all the parentheses. There's no more exponents. So now we're going to do multiply and divide from left to right. So 7 times 15 is, what is that? 105 minus 2 times negative 13 is negative 26. Or you can think of, this is the way that I think of it. I think of it as negative 2. See, this is, I would think of it as negative 2 times negative 13. Right? I don't rewrite this, but in my head. So negative and negative make positive, and then 26 plus 1. Now I'm going to add, subtract from left to right. So 105 plus 26 plus 1. And that equals 120, 132. And that's my final answer there. Okay, moving on to the next objective. Use the following properties of real numbers: commutative, associative, distributive, inverse, and identity. The commutative property of addition states that numbers may be added in any order without affecting the sum. So we write that in notation as a plus b is equal to b plus a. So we should have had some qualifiers. A and b are any real numbers. So these are properties of real numbers. Okay, so an example would be like 3 plus 5 is the same thing as 5 plus 3. We know that 3 plus 5 is 8. 5 plus 3 is also 8. Okay, so you can see that the order that you're adding the numbers doesn't affect the outcome. Okay, so that's the first one. And this also works with multiplication. So multiplication is also commutative. So if I had like 7 times 3, that's the same thing as 3 times 7. So the order doesn't matter. 21, you get 21 either way. Okay, and again, it's important to note that neither subtraction nor division is commutative. So, for example, if I did, all right, let's say 6 minus 2, and then you could see that if I did 2 minus 6, you could see 6 minus 2 is 4, but 2 minus 6 is negative 4, so those are not equal. Okay, and same thing with dividing. If I did 8 divided by 4, I get 2. And if I did 4 divided by 8, I get 0.5 or 1/2. So those are not equal. 8 divided by 4 is not equal to 4 divided by 8. Okay, so it's not commutative. Alright, the associative property of multiplication tells us that it doesn't matter how we group numbers when multiplying. We can move the grouping symbols to make calculation easier, and the product remains the same. So let's look at an example. Let's say I did something like 2 times 3 times 4. So our 4 basic math operations, add, subtract, multiply, divide, they're actually what we call binary operations. You need 2 numbers, so 2 times 3, for instance, will get us 6. Right? So we don't memorize multiplication tables 2 times 3 times 4 and know the answer. Right? We got to stop and we got to just do 2 at a time. So the associative property says if it's all multiplying, right, for associative property of multiplication, it doesn't matter how you group those 2 at a time. You could do the first 2. 2 times 3 is 6, and then 6 times 4 is 24. Or I could do it the other way around. If I had 2 times 3 times 4, I can group the 3 and 4 together first. 3 times 4 is 12, and then times the 2 is 24, and you get the same answer. I wrote these backwards from the way it's up here. So you can move that group around. So that's the associative property of multiplication. And it works with addition as well. Okay, so if we try something like, we'll use the same numbers, 2, 3, and 4. So if I did 2 plus 3 plus 4, and again, binary operations, I can only technically do 2 numbers at a time. So if I do 2 plus 3, here we'll do it using this property here. So 2 plus 3 plus 4. So if I do the 2 plus 3 first, I get 5. And then 5 plus 4, I get 9. And then let's look at it this way. So if we group the last two, 3 plus 4 is 7. And then 2 plus 7 is 9. And you see you get the same number. So that's the associative property. It doesn't, you can rearrange the group and it will still get you the same sum, provided it's all sum. So just like with the commutative property, it works for addition and multiplication, but not for division or subtraction. Okay, so the associative property doesn't work for subtraction or division. The division property states that the product of a factor times a sum is the sum of the factor times each term in the sum. Alright, so this is a pretty big one. So let's look at the numbers here. So if I had like 3 times 4 plus 5, we're saying that we can take 3 times each of the add-ins in that sum. So 3 times 4 and 3 times 5. So if we did this using order operations, 4 plus 5 is 9. And then 3 times 9 is 27. And let's see if that gets us the same result. So using the distributive property, we take the 3 and we're going to multiply it with each distributed. So 3 times 4 plus 3 times 5. So 3 times 4 is 12. 3 times 5 is 15. So 12 plus 15 is 27. And you can see you get the same answer. No, either way, right? So you can do it using order operations, or we can apply the distributive property and we can take that number that's being multiplied on the outside and multiply it with each of the individual add-ins and then add them together. Okay, the identity property of addition states that there's a unique number called the additive identity, which is 0, that when added to the number results in the original number. So the way we write this identity property is any number, so A can be any number plus 0 is equal to the original number, right? We should also write it the other way around. We know that addition is commutative, so 0 plus any number is also equal to itself. Okay? And the identity property of multiplication, so identity for multiplying is 1, and then any number times 1 is itself. Or again, because its multiplication is commutative, we could do it the other way around. 1 times any number is the same thing as any number times 1, which is just itself. Okay, so example, if we did like 5 plus 0, that's the same thing as 0. So this is kind of important concept as we get into algebra. We can say x is our variable, and then if we had x plus 0, we know that that's just x. We're going to use that all the time. And same thing with multiplying. If I did 1 times 7, that's 7. If I did 8 times 1, that's 8. And if I'm doing variables, 1 times x is just x. Or x times 1 is just x. I should use y. How about that? So if I did y times 1 is just y. Alright, so that's the identity property. So the identity for adding is 0. The identity for multiplying is 1. You should know that. The inverse property of addition states that for every real number a, there's a unique number called the additive inverse or opposite. So the opposite is the additive inverse. Those are the same thing. Okay, additive inverse is actually more broad of a term. But if we're talking about real numbers, the additive inverse is the same thing as the opposite. Now, if we're talking about other things, the additive inverse might be something else. Okay? So anyway, back to real numbers. The additive inverse, we're going to write it as negative a, or you should read this as the opposite of a, right? Because it's the additive inverse. So it's the opposite of a. So if you take any number and add it to its additive inverse, to its opposite, you're going to get 0. So for instance, if I took 5, the additive inverse of 5, or the opposite of 5, is negative 5. And 5 plus negative 5 is equal to 0. If I did 7, or let's do negative 7, the opposite of negative 7 is the same thing as 7, so that's the additive inverse. So negative 7 plus 7 is 0. The inverse property of multiplication holds for all real numbers except 0, because the reciprocal of 0 is not defined. So you got to know that. So 0 doesn't have a reciprocal when you're multiplying. And it states for every real number a, there's a unique number called the multiplicative inverse, or simply the reciprocal. Again, multiplicative inverse is a broader term. When we're talking about real numbers, the multiplicative inverse is the reciprocal. And we denote it as 1 over itself, 1 over the number. And if you take the original number, multiply it with its reciprocal, you're going to get 1, which is called the multiplicative identity. So if we took 7 times the reciprocal of 7, which is 1/7, those would cancel and you get 1. And if the number was a fraction, you do 1 over 2/3, which again, remember, this stands for reciprocal, so the reciprocal of 2/3 would be 3/2. You see you get 6 over 6, and 6 divided by 6 is just 1. Okay, so that's, oh, and then as far as signs, what if I did like negative 5? Now be careful, the reciprocal is 1 over negative 5. And when you're multiplying, negative times a negative makes positive. And then the 5's cancel, and you get 1. Okay, so same thing, like negative 5/8, the reciprocal would be negative 8/5. So you get 40 over 40, and negative negative make positive, and then you get 1. Here's a nice summary of all the properties of real numbers we just went over. So we got commutative property, right? Order doesn't matter, so that works for addition and multiplication. Associative property, we can change the grouping. Again, addition, multiplication. Notice there's no subtraction or division here. Distributive property, the identity property, and the inverse property. Okay, moving on to the next, evaluate algebraic expressions. And I know the lecture is going long, but it's recorded, so you can pause, take breaks. You know, I was thinking about breaking this up, but figure out you can pause it, take a break, come back to where you left off. And so I'll try to make them a little bit shorter, but anyway, I apologize for that. All right, I want to highlight some things from the book here. So the mathematical expressions we've seen have involved real numbers only. In mathematics, we see expressions like x plus 5, 4/3, pi, r cubed, or the square root of 2m to the third times n squared. In the expression x plus 5, 5 is called the constant, or a constant. Okay, so that's a big idea there, constant. It doesn't vary, right? So we say it's constant, stays the same. 5 is just a number. It has the same value no matter what. X, now you got to be careful. Sometimes we have letters that represent a constant. For instance, pi, that's a constant, even though it has a symbol there. But if it's representing a number that can change or vary, we call that a variable. Okay, variable. So x is a variable. Okay, and algebraic. Okay, so here's the definition: algebraic expression. It's just a collection of constants and variables joined together by algebraic operations of, your math stuff, right? Add, subtract, multiply, divide, and of course you can have powers and things like that, right? Okay, list the constants and variables for each algebraic expression. So again, our constants will be, here we'll make a little table here, constants. So that'll be 5. For this one, it'll be 4/3 and pi. Remember I said pi just represents a number that doesn't change, 3.14, so on. It's irrational. And then in this expression, square root's not a number or anything, so 2 is a constant. That's it. And then the variables, all right, variables, I'm just going to write var, x. And then in this one, the only variables are, and then this 3 is not a constant, it's a power, right? It's a power for the variables, so just ignore it. And same thing with the square root. It's just a math operation. It's kind of like a power, actually. So we got m and n as our variables here. M and n. Okay, example 9. Evaluate an algebraic expression at different values. So evaluate the expression 2x minus 7 for each value of x. So I added this here. To evaluate an expression, that just means, evaluate simply means get a value for it. Figure out what the value is, right? So to do it, you're just going to substitute the given values for the variables, right? If there's more than one, you put them in for all of them, and calculate using order operations. All right, so let's try a couple of these. So for A, if x is 1, 2x minus 7. Okay, so if x is 1, oh, I'm sorry, x is 0, you just plug in 0 for the x, and then you work it out to order operations. So we do in the parentheses, there's nothing to do there. So exponents, no exponents, multiply, so that's 0. And then subtract 0 minus 7, it's just negative 7. All right, let's try B. 2x minus 7. I'm going to write 4x equals 1. So we take the x out, put in 1. Now get in this habit of putting a parenthesis when you substitute. If there's negative numbers and things, it can help. It can keep you from making a simple mistake with signs. So this is a good habit to get into. Just put a blank parenthesis for the variable, and then substitute, plug in the number that's given for that variable. Okay, order operations again. There's again, I'm not thinking this is a grouping symbol now since it's just one number, right? There's nothing to do. So we can skip that. There's no exponents. Multiply. 2 times 1 is 2. 2 minus 7 is negative 5. Oh yeah, so I'd like you to box your answers. All right, let's try one more. Let's do D. I guess I could have done both of them. So 2x minus 7 for x is -4. So 2 times -4. This is what I'm saying. If you do parentheses, right, you're not going to confuse this as 2 minus 4. It's 2 times -4. So that's -8. And -8 plus negative. So again, in my head, without rewriting this, I'm thinking as -8 plus -7. If both signs are negative, you add the numbers, the absolute value of the numbers. So 8 plus 7 is 15, and then you keep the sign, so it'll be -15. All right, so there's some Math 85 review for you. Okay, and on to our last learning objective for today's lesson, simplify algebraic expressions. So sometimes we can simplify an algebraic expression to make it easier or to evaluate, make it easier to evaluate or to use in some other way. To do so, we use the properties of real numbers. We can use the same properties and formulas because they contain algebraic expressions. So basically, I think of simplifying as just can you write it more simply, right? Is there another way? So for instance, if it's just whole numbers, 3 plus 5, that's an expression, right? But you can write it more simply by figuring out 3 plus 5, that's the same thing as 8, right? So that's simplifying. So 8 is more simple than 3 plus 5. Now you do that with algebraic expressions with variables and all that. So let's look at some examples there. Okay, let's start with A. So 3x minus 2y plus x minus 3y minus 7. Okay, so in a beginning algebra class, right, we have all these properties that we just talked about, the associative and commutative and all that, and the distributive properties. So what we could do is we're going to think of this as, normally you don't write this down, but we want to think of everything as addition, because then we have all the commutative properties. So normally we don't write this, but in our head we're thinking this. Okay, so everything's in terms of addition, so I can rearrange the order. Put my x's together, put my y's together. I'm going to leave those in parentheses since they're negatives. Now, we have associative properties, so we can group things. So I can look at these, and I can do the distributive property in reverse and pull out a 3. Oops, I don't know what I just did. Oh no, sorry. I'm not going to pull out the 3. I'm going to pull out the x. I'm going to distribute the x. So, oops. Okay, so I'm going to factor out the x. Now, because of the identity property, we can think of this as 1 times x. So I'm going to factor out the x, which is the opposite. We're doing the commutative property in reverse. And same thing for here. I'm going to factor out the y. So I got -2 plus -3. And again, we don't show all these steps. And then 3 plus 1 is 4. So that's how you combine like terms, is you're really doing the distributive property. -2 and -3 is -5. And then again, multiplication's commutative, so I can switch the order. Right, and it's easier to write, instead of writing plus -5, it's easier to write -5. Same thing. So this is that same expression, more simple. So I simplified it. So I was just showing all the, all the properties that we just went over in there. So typically when you simplify this, the way you would write it, you go basically 3x plus x is 4x, minus 2y plus negative 3y is minus 5y, and then minus 7. You don't have to show any of that work. All right, let's try B now. So let's see, I'm going to do 2r minus 5 times 3 minus r plus 4. I'm not going to show all the detail like there. Okay, my first step is I can distribute that. I'm going to think of this as plus and negative 5. I'm going to go ahead and write it. And I'm going to distribute negative 5. So negative 5 times 3 is negative 15. Negative 5 times negative r is positive 5r. Then I got the plus 4. I'm going to combine my like terms. 2r plus 5r is 7r. And then negative 15 plus positive 4 is negative 11. And then that's my answer. Okay, I think that's enough. So that will conclude the lesson for the first one. As far as just read the syllabus, make sure you know what to do for the homework assignment, and I will see you soon.